Hello everyone, welcome to Organic Chemistry Tutorials. Today we'll be talking about Alkene addition, part 2. So before we proceed, it's very important that you watch part 1 because this part will not make sense if you do not watch it. So the next reaction we're going to talk about is oxymercuration, demercuration, and we'll just call this OD. So this adds water across the double bond similar to acid-catalyzed hydration. Unlike acid-catalyzed hydration, OD proceeds via anti-addition and carbocation rearrangement is not possible during this process. So OD proceeds via Markovnikov addition, anti-addition, and carbocation rearrangement is not possible. So these are the reagents we're going to use. Pay special attention to the numbers. You are required to put those numbers. So we're going to add across the double bond via Markovnikov addition. This carbon is tertiary because it's attached to 3 other carbons. And this carbon is secondary because it's attached to 2 other carbons. So this carbon is going to get the hydroxyl group and the other one's going to get the hydrogen. And notice how they are on opposite sides of the plane because we are adding via anti-addition. Next, we have hydroboration oxidation, and this also adds water across the double bond. And so this is the last hydration technique along with acid-catalyzed hydration and OD. This proceeds via anti-Markovnikov addition and syn addition, and carbocation rearrangement does not occur. So here are the reagents we'll use for hydroboration oxidation. And remember, this is our tertiary carbon, this is our secondary carbon. So we're going to proceed via anti-Markovnikov addition. So the less substituted carbon is going to get the hydroxyl group. And because we're proceeding via syn addition, these should be on the same side of the plane. So let's do an example. So first we're asked to use oxymercuration, demercuration on this alkene. So remember that is Markovnikov and anti-addition. So this is the tertiary carbon and this is the secondary carbon. So that means the tertiary one, because we are proceeding via Markovnikov, is going to get the hydroxyl group, and the secondary one is going to get the hydrogen, and they both have to be on opposite sides of the plane because we are adding via anti-addition. And I'm just going to write plus En for the other enantiomer that results from this. Next, we need to add water via hydroboration oxidation, which is anti-Markovnikov and syn addition. So that means the secondary carbon is going to get the hydroxyl group, and the tertiary one is going to get the hydrogen. And I'll just write plus enantiomer for the other enantiomer that results from this. And that's it. So sometimes dashes and wedges aren't needed, in particular when you don't have a chiral center. So let me show you what I mean by that. So here we're using hydroboration oxidation to add water to this alkene. So we're going to add via anti-Markovnikov addition, and you might be tempted to put a dash and a wedge, but you don't have a chiral center anywhere here, so there's no point in putting dashes and wedges. The next reaction is catalytic hydrogenation. So we're going to add two hydrogens across a double bond. We're not going to care about regioselectivity because we're adding the same thing across the double bond, and this reaction proceeds via syn addition. It also requires a metal catalyst, and that can be platinum, palladium, or nickel. So for catalytic hydrogenation, you can choose whether or not to show the hydrogens. So on the top, we have the products if I were to show the hydrogens, and on the bottom, we have the products if I chose not to show the hydrogens. So for catalytic hydrogenation, you have to be careful because it's sometimes possible you'll get a mesostructure. So what I mean by that is you might be tempted to say that these two are different molecules, but they're actually mesostructures, so they represent the same molecule, and you can see that by this line that indicates the molecule is symmetrical. So next up we have halogenation, and in this case we're going to add two bromines or two chlorines across the double bond. Regioselectivity is irrelevant, and this reaction proceeds via anti-addition. So the reagents we're going to use are bromine Br2 or chlorine Cl2 and a non-reactive solvent such as CCl4. This is non-reactive. Next up we have halohydrin formation, and this is the addition of either bromine or chlorine and an OH group. So the OH group gets attached to the more substituted position, while the bromine or chlorine gets attached to the less substituted position. And this reaction also proceeds via anti-addition. So you can see in this case that the OH got attached to the tertiary carbon and the halogen got attached to the secondary carbon. And you can also see the anti-addition in this case as well. So next up we have anti-dihydroxylation, and in this case we're going to add two OHs across the double bond. Regioselectivity is not going to be important because we're adding the same things across the double bond, and this proceeds via anti-addition, as implied by its name. So first we're going to use a peroxy acid, such as MCPBA, and we're going to follow that up with hydronium, and we usually get this hydronium from an acidic source, such as sulfuric acid, but you can just write hydronium. And finally, we have syn dihydroxylation. This is basically the exact same thing as anti-dihydroxylation, except we're going to proceed via syn addition, as implied by its name. So we got two sets of chemicals we can use here. We can use this set of chemicals, where first we use osmium tetroxide, which is a toxic chemical. And then we can follow that up with a workup of sodium bisulfite and water. So if you don't want to use osmium tetroxide, what you can use instead is potassium permanganate and sodium hydroxide under cold conditions. So let's do one more example to solidify our understanding of the material. So here we have the reagents used for anti-dihydroxylation. And so that means we're going to add two OHs across the double bond in an anti-fashion. So let's draw our alkene, and then let's draw our two OH groups. So now the question is, how can we show stereochemistry? Because that's very important, because remember, we're going to have to add via anti-addition. So you might be tempted to draw something like this. But this is actually not the correct answer. In fact, this carbon right here is not chiral. So you don't need to show the dashes and wedges on that carbon. However, this carbon is chiral, so you do need to show the dashes and wedges on that carbon. So what my final answer should be is this, plus the enantiomer that can result from that. Okay? So just be on the lookout for chiral carbons, because that's going to be very important for your final answer.